Good day, everyone. I'm Guy Patrick, and I'd like to welcome you all to today's webinar on PFAS in the environment, sources, behavior, and remediation at infrastructure, manufacturing, and waste sites. Today's webinar is the second part of a three-part series. It's going to be presented by Stefano Marcanetto and Ross Bennett, both of Golder Associates. Stefano is a senior environmental engineer and associate in Ottawa, Canada, and he's Golder's global PFAS practice leader. He has over 10 years of experience with site characterization, risk assessment, and remediation at PFAS contaminated sites, including airports, military bases, firefighter training areas, manufacturing facilities, and landfills. He works across North America and overseas. And joining him today is Ross Bennett. Ross is an engineer who's licensed in the state of New Hampshire in the US. He has 15 years of experience in engineering, site investigation, and conceptual site model development for remedial activities at contaminated sites across the US. He leads Golder's team addressing the occurrence, fate, and transport and management and remediation of emerging contaminants, including PFAS and other substances such as 1,4-dioxane. His recent experience includes several large sites where emerging contaminants have forced the reevaluation of site investigation activities and remedial strategies. So before we get going, a word about this webinar. We're going to go for about an hour. We've structured it so there should be time at the end for questions. So please feel free to type in the questions from the question panel. I think you punch a button on your screen with your mouse, type it in, and I'll be monitoring those things. So at the end, we can have a bit of a dialogue. And I'll go over the questions with the panels. So now I'd like to turn it over to you, Stefano.
Thanks a lot, Guy, and thanks everybody for joining. So today we are going to talk about AFFF and manufacturing sites as two of the primary areas that have PFAS issues to deal with. First of all, we'll look again at the basic chemistry of PFAS. For the ones of you that joined part one of the webinar, this is a repetition, but just in case somebody that is here today wasn't there last week. This is the PFAS family tree, where you can see the big PFAS class is divided into perfluorinated and polyfluorinated compounds. The perfluorinated class has all the hydrogen replaced by fluorine along the alkyl chain, so you have carbon and fluorine bonds. And the polyfluorinated still have some carbon and hydrogen bonds left. Then if you follow the orange part of the chart, you see that the one subclass of the perfluorinated compounds is what they're called perfluoroalkyl acids. And this is the focus of today's discussion and most of the focus of the PFAS discussion that you hear these days. And this class of compounds, also known as PFFAs, are divided into two subfamilies, the carboxylate and the sulfonates. The carboxylate include PFOA and all the other compounds that end with A, and the sulfonates include PFAS, as well as all the others that end with S. And then you have everything else that is not orange in this family tree that belongs to the class of precursors. So while the perfluoroalkyl acids don't really biotransform in the environment, and therefore they're called terminal PFAS, all the precursors under the right environmental condition can actually biotransform to perfluoroalkyl acids. And while the perfluoroalkyl acids typically analyzed by commercial laboratories these days are in the 30 or so compounds, the polyfluorinated portion of the family or the precursors are actually in the thousands. So the number of molecules that we actually analyze every time we do this type of investigation in terms of individual compounds, it's only about a small percentage of the entire family. In terms of uses, PFAS has been around since the 1940s, 1950s. And most of the focus these days is around AFFF, or aqueous film-forming foam, and therefore they use in PFAS in firefighting foams. But they've been used in many different sectors of the industry for a very long time. And this slide shows some of those various uses. So it ranges from automotive, electronics industry, to resource extraction in the oil and gas industry, semiconductors, as well as building construction. Like, believe it or not, you also find PFAS in concrete to increase the UV resistance of the material, as well as reduce the corrosion potential. And in general, most of the products that are water repellent, soil repellent, or oil repellent are likely to have been produced using PFAS in the past, or replacement compounds of PFAS currently. Sources are typically divided into point sources and non-point sources. Point sources, in general, are primarily firefighting facilities or areas with high potential or history of fuel fires related to the AFFF use, manufacturing plants, as well as landfills and wastewater treatment plants. We have non-point sources that can include biosolid applications, atmospheric deposition, as well as surface water runoff from contaminated lands or streets. In addition to these most common sources, there are lots of emerging sources that we have to deal with, and these sources that are not as well known to produce PFAS, but we find this in every day during our investigations. And these include car washes, junkyards, facilities that deal with cutting and sealing of granite or stones, carpet cleaning facilities, facilities that deal with automotive detailing because of the wax used for those, as well as building construction material, as briefly mentioned before, and so septic systems.
Hey, Stefano, just a comment there on those emerging sources.
Right.
By emerging, these are sources that we're just recognizing, but they've been around for a long time, I take it. Is that correct?
Correct, yes. These products have been used for a very long time, and they only came to the public attention in the last 10 years or so, and in some jurisdiction even later than that. So these products have been used probably for decades in all these sites. It's just now that we recognize their use as those sites and have to deal with the consequences of that.
Okay, thanks.
So in terms of AFFF, we need to be aware that the composition of AFFF has changed over time. The production process has actually changed itself. First, most of the AFFF and the PFAS, including the AFFF, was produced by electrochemical fluorination. And then in the last 15 years or so, changed to telomerization process. And what that means is that from 1960 to about 2001, 2002, most of the foam that contained PFAS was based on what we call the C8 compounds, and primarily PFAS. That is one of the most well-known PFAS these days. In addition to PFAS, they had long-chain precursors that over time and in the right environmental condition could actually biotransform to the C8 and the C6 sulfonates, so to the PFAS and the PFHXS. And this was phased out, the production of these foams was phased out in about 2001, 2002. And that's when fluorotelomere-based foams started to flood the market. They were produced originally since the 70s, but not used that much. But the early version of the fluorotelomere-based foams primarily contain still the PFHXS, as well as precursors that in this case could biotransform to PFOAs and some of the other carboxylate. And these were used approximately until 2016. And the reason they transitioned to this foam is because of the toxicity information. At that time, PFAS was considered more toxic than the shorter chain, the C6 sulfonates. So by eliminating PFAS, they tried to reduce the problem. But then as time went on and more research was conducted, the toxicity information about some of the shorter chain compounds was also developed that put some uncertainty as to whether they are actually much less toxic than the original compounds. And so the next step for the fluorotellumer-based foam was to use short-chain PFAS and precursors that could only degrade to short-chain PFAS. So that's what we see used mostly these days, with lots of research as well as testing done on what they're called F3 or fluorine-free foams. And these foams do not contain any fluorocarbons. And the main issue is to make sure that they can extinguish the fire within the same parameters that are needed to deal with potential accident as the fluoropolymer-based foams, and also making sure they don't have any other toxicity associated with them due to other compounds or the elevated VOD that they can create once they are discharged to surface water. And in terms of AFFF sites, there are several sites to consider. Most of the ones that are under investigation right now in various jurisdictions around the world are airports, military bases, Navy ships, firefighting training areas, fire stations, as well as sites with a history of fires or potential combustion, since AFFF was often used also to prevent combustion from potential spills or leaks. But then there are several other sites that have similar problem because of the use and storage of AFFF. That those are oil refineries, terminals, rail yards, some of manufacturing facility, and even mine sites. Because of the various type of uses of AFFF at each site, there is potential for several PFAS sources at each AFFF sites. You can have AFFF releases to the environment directly from training, typically in firefighting training facility, but it could also be as part of firefighting and fire prevention, as we just said. But then there is the whole problem about malfunctioning systems, maintenance and testing of fire suppression system and equipment to be done regularly, potential leaks or spillage for AFFF storage tanks, as well as the whole issue related to wastewater, stormwater discharge associated with any of these potential uses. And then the last one, that is the one that makes the issue even more complicated for us environmental professionals, is the issue associated with historic remediation of some of these sites or sources because of other contaminants. And we'll see later how actually remediation using some of the conventional technology can make the PFAS problem worse. And a couple of points to highlight on this slide still is that when we talk about AFFF, we can talk about the concentrate, so the material that is actually mixed with water to produce foam, or with foam solution. And as you can tell, the release between the two is very different, both in terms of volume as well as in terms of PFAS concentration. And when AFFF are actually used for training or to fight the fire, there are large volumes of water involved. So for most of the sites that we work at, we often find the issue related to contaminant migration is because of surface water runoff or migration via storm or sanitary sewer system, or directly to surface water. So the hydrology component of the site is extremely important to deal with the conceptual site model for these sites. In terms of other PFAS uses and sites, as I briefly mentioned, PFAS has been used for decades in many manufacturing processes, but there are specific PFAS that were used depending on the application. And similarly to what we have seen for AFFF, also the PFAS chemistry has changed over time for these uses. Same as AFFF, it all started with the C8, so the PFOS and the PFOA. And then because of the toxicity, there has been lots of push in terms of replacement chemistry. So they started to use fluorotelomers and the C6. With the fluorotelomers, though, that could actually biotransform to the C8. So not quite solve the problem because introduced some of the precursors that could actually produce the C8, even though the C8 were not directly used. But then the next step was to develop other replacement compounds, such as Gen X or Radona that you may have heard. Those are brand names for some precursor compounds that are supposed to be less toxic than the original ones. And then lastly, there is a move to use fluorine-free products. And because of their widespread use for so many years, and the fact that PFAS can be released to the environment from manufacturing facilities and other processes, we end up finding PFAS in many consumer products and material. And Ross later on is going to talk a little more about that part. And then because of those two things combined, they use in manufacturing facilities as well as the presence of PFAS in so many consumer products, you end up with PFAS in landfill leachate, wastewater treatment plants, and biosolids. As I mentioned before, the PFAS vary depending on the use in the various sectors and industry, as well as there are specific release mechanisms in the various industry and sectors. And when I mean release mechanism, is primarily to the environment. And this slide shows example of 4 sites where you can find PFAS. I won't go into detail for each of those, but if you can just focus on the 2 on the right-hand side, in terms of the PFAS use, most of the firefighting training area are dealing with C6 to C8 sulfonates, so the PFAS and the PFHXS, and as well as fluorotelomers sulfonates. You have potential for NAPOL at these sites because of the use of fuel to light the fire, as well as potentially dissolved phase hydrocarbon and solvents, particularly down gradient of your source area or firefighting training area. And if you compare that with that landfill instead, typically in landfill you have a mixture of PFAS because of the various materials that have been stored at these sites, and concentration of short-chain PFAS are typically dominant as opposed to very specific type of long-chain PFAS. And then you also have release of other contaminants such as metals and others. In terms of release mechanisms, we'll get into detail later, but what you see at firefighting training areas, it primarily has to do with spraying of the foam potentially outside the containment area, as well as leaks and spill. Whereas in landfills, primarily still with leachate and surface water runoff. And because of the specific use of PFAS, depending on the ultimate goal and facility, you can actually identify specific signature of PFAS at the various sites. And this slide summarizes what we have noticed at 4 different sites. So there are 2 manufacturing facilities at the top, firefighting training area at the bottom left, and then landfill of the bottom right. And each of the plot show the PFAS along the perimeter, the concentration on the radial axis, and each shape of each plot, it's a specific water sample in this case. And you can use this system to compare signature within a site to identify potential different sources, or at least have an indication that there could be different sources, as well as compare signature between sites and develop signature libraries like we are doing. In terms of fate and transport property for PFAS, it's very important to distinguish between the terminal PFAS of the perfluoroalkyl acids that we've been talking about and the precursors. The PFFAs are usually present in the environment in the anionic form. They have very high water solubility, low vapor pressure, they are not retarded very much, they are not biodegradable, and they are bioaccumulative. As a consequence of this, they are persistent, they can travel long distances, and typically the concentration increase with the increase in trophic level along the food chain, also because some of them biomagnify. And typically the short chain PFFAs are more mobile than the longer chains. If we look at the precursor, we have this big family of 3,000 plus compounds that can include very different molecules with different properties. So you have some that are positive charged, some that are negative, some can have both charges. And as a consequence, some can actually soar more to soil than the terminal PFAS, and some are also volatile. So when you hear about PFAS not being volatile, that's true, but only related to the terminal PFAS. If you look at some of the precursors, they can actually be quite volatile. And because they are fairly persistent, they can travel long distance, and they can biotransform over time to the terminal PFAS. So some of the research studies that have been completed about PFAS concentration in very remote locations, you can actually find terminal PFAS in those locations, not only because of the direct release of terminal PFAS, but because of the release of precursors specific in the atmosphere, and then biotransformation to generate the terminal PFAS. And because of the high absorption to soil for some of the precursors, there is the potential to have very long-term sources that can slowly, in the right environmental condition, break down to the terminal PFAS over time. So at sites where you're dealing with risk assessment, but particularly with feasibility assessment for any sort of remediation, is extremely important to be able to characterize the full mass of PFAS at your site, because if you're only measuring the terminal PFAS and dealing with those, you may end up ignoring a potential source area primarily made up of precursors that could feed terminal PFAS over time. And then the part that I was mentioning earlier about historical remediation is that the precursor can biotransform in the environment, but can also biotransform because of some of the processes that we use during conventional remediation of other contaminants. So for example, if we consider in situ chemical oxidation or enhanced biodegradation, or even land farming or biopiles, all these techniques produce oxygen or generate conditions that promote the transformation of precursors into terminal PFAS. So when these were done to deal with hydrocarbons, for example, or some solvents, and you also had PFAS without knowing it at that time, you may have transformed some of the precursors that maybe were more sorbed to soil at that time into terminal PFAS that are more mobile and more toxic as well. And on this slide, we just show a quick overview of some of the fate and transfer processes that we just talked about. So from right to left, you see 4 monitoring wells. The first one to the right is actually upgradient of the source area. And then you have the second one from the right is in the source area, and 2 of the other ones are downgraded of the source area. And we plotted the PFAS signature in groundwater at this location. And first of all, you can see that in the well that is upstream of the source area, you do have some PFAS detections because primarily in this case was groundwater flow direction changes over season and over the years. But then if you look at the plots for the wells that are on the left, you actually see the PFAS signature changes as the plume migrates to the west. And if you pay specific attention to the C8 and C6 sulfonates, so if you look at the PFAS and the PFHXS, you can see that the PFAS concentration changes quite a bit between the three locations, in particular between the source area location and the most down gradient location. But the PFH excess, it's almost similar. Like the changes is much more subtle. And because the PFAS and the longer chain compounds is retarded more by the aquifer as it travels downstream, is actually moving slower than the cis-X sulfonates. And so is true also for the shorter chain compounds, shorter than the cis-X. And you can actually use some of those shorter chain results, even though you may not use those results for comparisons to standards because those compounds may not be regulated yet, but they are actually quite useful in terms of predicting PFAS migration and flow pathways. And the similar process can be used to assess partitioning uptake in various media. We have done it for soil, groundwater, various terrestrial receptors, sediment, surface water, and so forth. But this slide shows what we have done in terms of uptake and partitioning in aquatic receptors. So the plot on the top left shows benthic invertebrate, and the other two plots show small-bodied fish and large-bodied fish collected from the same area. And without going into much details, you can see how the different uptake of the different compounds based on chain length and other properties is quite different between the various species.
Oh, Stefano, just doing a time check here. We're about halfway through now.
Thanks, guys. Okay, so let's talk about investigation planning and design right now. So the part to consider, like for every environmental investigation, includes site settings, infrastructure. In these cases is especially important because of the potential surface water pathway and preferential flow. So look at infrastructure both above and below ground, as well as former infrastructure, details of operation, type, quantity, and frequency, and date of the PFAS use, as well as the PFAS release mechanisms that we talked about before. And then the approach of the investigation based on the changes depending on the specific conceptual site model. But our strong recommendation is to include background location, background sampling for all media because of the diffuse nature of PFAS detections. You want to make sure that you have a good understanding of what you see at your site in terms of background. And you should sample shallow soil for sites where PFAS releases occur at the ground surface. And you should also focus at phase boundaries. So at the water table, at the sediment surface water interface, because the PFAS like to stratify, and therefore they could be present at higher concentration at phase boundaries. And as it's obvious now, based on what we discussed before, you should consider the presence of other contaminants as well as historical remediation at the site that could have changed the picture quite a bit. And in terms of which type of receptor to focus on, most of the issues are related to toxicity for drinking water as well as surface water for ecological receptors. So these are the two media to focus on primarily. And because of these compounds are very mobile, you often have to deal with large plumes and multi-property contamination, and you have to be prepared to deal with that. And because of this as well, because of the large plumes, it's often quite lengthy to fully characterize your site from start to finish. So the recommendation and accepted practice now is that if exceedances are identified near the source area and you have enough supporting evidence to suggest that there aren't other sources of PFAS at that site, it's best to look near receptors to assess the risk first and then refine the characterization later. In terms of investigation design, specifically for fire training areas, this slide shows some parameters to consider. First of all is whether there is a liner or not at the facility, as well as the type of liner, because some PFAS can actually sorb to some liners and therefore can be a long-term source to the environment. Then we have to look at whether foam spraying occurred beyond the limit of the training area, so direct impacts outside the area. Consider air transport and therefore prevalent wind direction. And consider all the drainage system. Because of what we discussed before, surface water discharge is going to be a big issue, and groundwater surface water interaction therefore become a key consideration, as well as the potential for source zone away from the main release. Because of this migration through storm or sanitary sewer or surface water bodies, you can actually find, depending whether it's a gaining or losing stream, that sources can actually be located away from the main release and keep feeding the groundwater from those areas. Then you should consider wastewater treatment systems, whether they are on site or off site, and actually check if they're effective, because most of the conventional treatment systems are not effective to deal with PFAS, as well as historic site treatment of hydrocarbon or other impacted soil, as we mentioned. And it's really useful if you can to observe the training exercise live, so that you can get lots of details out of that, as well as always do a mass balance and the water balance specifically, since some of the leaks may not be visible, but may have occurred over a long period of time. So I'll finish my part just covering two quick case studies related to AFFF investigations. So the first one is a fire training area. And as you can see in these photos, and many fire training areas, the AFFF is discharged on surface away from or beyond the limits of the fire training area that is, in this case, lined. And in this site in Canada, you can see at the bottom photo, how the surface water level within the facility is so close to ground surface. So it's not difficult to predict that any further rise in water level can actually be a big issue for groundwater impacts. And at this specific site, we also had an issue with the stormwater wastewater discharge. As you can see in these photos, one of the manholes controlling the water level in the facility was malfunctioning, and therefore you had liquid from the facility crossing a road and flowing downstream towards a creek and discharging directly into a creek. And some of the PFAS release mechanisms that we had to focus on was direct spraying beyond the containment system, wind-driven particle transport and deposition on soil away from the fire training area, as well as the typical issue of stormwater and wastewater in terms of overflow as well as leaks. And what we did at this site to actually assess whether the surface water PFAS issue that we were seeing were primarily due to ongoing groundwater impacted PFAS impacted groundwater discharge to surface water, or to dissolution of PFAS from sediment. We compare PFAS signature in these three different media, and as you can see, the surface water signature is quite defined, and it doesn't really match the sediment signature. But then we collect the groundwater sample from the 3 wells that you see in the figure, and the color in the plot resembles the color of the wells, and you can actually see that as you move close to the creek, the groundwater signature it's almost identical to the signature of the surface water, even though it's order of magnitude different. So this was one line of evidence that started to indicate that groundwater discharge to the creek is actually the primary pathway to deal with, as opposed to dissolution of PFAS from sediment. And this other case study instead was a very large site where the client was required to develop mitigation measures to deal with several different PFAS sources, with the key pathway still being PFAS via stormwater. And so our objective was to develop an efficient approach to identify the main sources, as well as assess their contribution, and being able to prioritize them and address them to reduce the discharge. So we developed a stormwater sampling program, a specific key nodes within the stormwater drainage networks. We selected those sample locations based on the catchment areas, as well as the source locations that we were aware of. We use hydrous leaves to sample stormwater, and I will show you in a second. And then we converted the concentration into mass discharge per year at each of these nodes and facilities. And thanks to this approach, we were able to complete the program in less than a month. We were able to fill almost all the hydrous leaves, and you can see a photo of the hydrous leaves on the right-hand side. And most importantly, we were able to identify the most problematic areas that dealt with residual PFAS concentration in AFFF, despite a removal program. And this is quite typical at various sites because it's very difficult to fully clean tanks and equipment and remove all PFAS containing foams, as well as associated with training activities outside of the fire training area that even the client wasn't really quite aware of. So ultimately, we produced this figure where the different colors show the different relative mass contribution in grams per year of PFAS. And the fire training facility was actually the main one, but we found, as I mentioned, a few other facilities that were key contributors, and we had to deal with, and successfully did so in a very quick period of time to reduce the discharge to stormwater. With this, I'm going to end my part, and I'll turn it over to Ross, and he's going to cover the manufacturing part of the presentation.
Right. Thanks, Stefano. So it's starting off with manufacturing, and this is a little bit of a repeat of some of Stefano's slides earlier, so I may go over it a little quickly in the interest of time. But you know, PFAS have been used since the 1950s in a number of applications because of their versatile properties. Industrial applications include fluoropolymer production and application for products such as Teflon, Gore-Tex, Stainmaster, Scotchgard, and also in metal plating facilities, electronic and semiconductor applications, aviation hydraulic fluid, oil mining production, and a number of other industrial applications. They're used in a number of consumer products listed at the bottom of this slide. You know, one of the reasons they were used so widely is because they have some really unique chemical properties. Specifically, the PFAS molecule has at least a perfluorinated molecule has a hydrophobic head, which is a functional group, and a nonpolar tail, which is the alkyl chain that makes it both hydrophobic and aleophobic. And because of these properties, they prefer to stay along phase boundaries at the air-water interface and stratify in solution. And they also like to adhere to surfaces. So they were widely used because of these properties, but these same properties that made PFAS so useful in industry is a lot of what makes them a challenge to investigate or remediate and manage at PFAS sites today. Specific to manufacturing, most PFAS sources at manufacturing facilities would be point sources, and there are really two classes of PFAS manufacturing facilities. There are the primary producers, the facilities producing PFAS, and then the facilities that are using PFAS or PFAS-containing materials in their manufacturing processes. There's a graphic on this slide from ITRC's conceptual model for PFAS that shows some of the typical release pathways for manufacturing facilities, which include air emissions, spills and leaks, waste and wastewater disposal, stormwater, discharge and runoff, and firefighting training facilities, which can exist at larger manufacturing facilities. Production of, as Stefano mentioned earlier, you know, long chain PFAS have largely been phased out, but emissions of precursors and short chain PFAS may be ongoing at some facilities. And one of the biggest challenges for manufacturers right now would be the regulatory challenges. There's a lot of awareness around PFAS right now because of its regulation in drinking water or groundwater. You know, there are a number, there's the US EPA Health Advisory of 70 parts per trillion. And then there are a number of state guidance values or enforceable values. Probably one of the most notable of which is December of last year, New York's Drinking Water Council recommended a 10 part per trillion MCL for PFOA and PFOS. But aside from the actual regulation in drinking water and groundwater, there are a number of emergent regulatory fronts that present challenges to manufacturers, including surface water. For the most part, most states and federal governments or provinces don't regulate PFAS in surface water at this time. So there's a lot of uncertainty on that front. Wastewater, it's also largely unregulated in wastewater. It's not currently, at least here in the US, not currently regulated as a hazardous waste under, you know, CERCLA or RCRA legislation. But there is, at this time, there is a proposed legislation to identify PFAS as a CERCLA hazardous substance in the US. And then in the US at the state level, there are some laws, for example, California's Proposition 65, which requires employee notification requirements for materials that contain PFAS. All of these emerging regulatory fronts create a big challenge for manufacturers who are trying to figure out how to use and how to manage these materials that are so widely used. As an example of a regulatory challenge, this is I guess I'll call it a hypothetical situation of a manufacturing facility that has a groundwater treatment system in place. It's operating an active manufacturing facility because of legacy VOC impacts. If that treatment system were to be sampled for PFAS, and PFAS was detected in the influent and the effluent, and that treatment system is discharging to surface water, you know, the question will be what to do next, and some considerations that would be important to take into account when making a decision is that PFAS is not currently covered under most federal surface water discharge permits. It's not, most states and provinces are not regulating PFAS in surface water, and the treatment costs are high. So it's hard to justify implementing a measure to address PFAS in this treatment system discharge within the context of all the regulatory uncertainty, even though the numbers can be high in a situation like this. Case study for a manufacturing facility for a chromium plating facility. This is a facility where PFAS were used as a mist suppressant in the chrome plating process. The site is around 10,000 square meters or 100,000 square feet. And it has a long industrial history in operation since 1905 and began plating in the 1940s. PFAS is investigated in groundwater across the site, including PFOS at up to 13,000 nanograms per liter. That's relative to a US EPA health advisory of 70 nanograms per liter. And PFBS was detected up to 2,400 nanograms per liter. And just for comparison, hexavalent chromium was detected at 76,000 micrograms per liter in similar groundwater wells. After characterizing the facility, the client embarked on remediation, which included decommissioning the buildings and underground tanks at the facility, approximately 2,000 cubic meters of soil excavation, and groundwater treatment, consisting of pump and treat with treatment specifically for PFAS using granular activated carbon. An interesting sidebar for this investigation is that we used a unique analytical method to look at ultra short chain PFAS. These are the C2 or C3 short chain sulfonates. and found them at relatively high concentrations, 6,000 to 40,000 nanograms per liter. These are compounds that are not typically analyzed for under commercial laboratory methods like EPA's method 537. And they're certainly, I'll call them compounds of emerging concern.
Hey, Ross, is that picture there? It looks kind of that yellowy, greeny chrome look about it. Is that a chrome release that we're looking at?
Yeah, surface soil impacts.
All right.
Case study 2, we're looking at source differentiation for PFAS impacts. This is significant because PFAS have been released from multiple manufacturing facilities, and public water connections are being required for residential properties with PFAS impacts in private wells near these manufacturing facilities. And because PFAS are being regulated at lower and lower levels, 70 parts per trillion here in the US and lower in individual states here in the US, this becomes a challenge because numerous other PFAS sources can be present in the vicinity of these manufacturing sources. So it's essential to be able to differentiate between PFAS impacts related to a manufacturing source and other sources. And the next slide shows, just as an example, a set of mostly drinking water well results and some monitoring well results in a relatively rural area of the northeastern United States. And this is just kind of to underscore the kind of anthropogenic background that can occur when you look for PFAS in relatively well-developed areas. The purple dots at the top of the screen represent a rural fire station with PFAS detections, PFOA plus PFOS greater than 400 parts per trillion. The red dot, about a third way of the way down the middle of the screen, represents a former car wash facility where PFAS has been detected in the hundreds of parts per trillion. And the red dots towards the bottom of the screen, or the red dot, represents a former automotive maintenance facility. And those are, traditional site investigations that are ongoing at those facilities. But what is of significance is a lot of the yellow dots, especially on the left or western half of the screen. Those are all values in the 10 to 20 parts per trillion range in residential wells in very rural areas. If you're thinking about things like New York State's proposed 10 part per trillion MCL, those wells would require treatment. And it would be very difficult to determine what of all the potential sources that could be present within this screenshot could be causing driving that need for treatment. So Golder's developed a tool that allows us, that Stefano showed some screenshots of before, that allows us to differentiate source based on the suite of PFAS present in a sample. And this is an example from a manufacturing facility that had wastewater samples, which are the blue and red and gray lines, and one sample from a nearby residential well, which is the orange line, which has a very similar signature in terms of the suite and ratio of compounds detected to the wastewater samples at the manufacturing facility. But then the green line represents a well in a surface mine approximately 2,000 feet away from this facility. It has a very, very unique signature, a very distinguishable signature from the manufacturing facility, and in fact includes significant detections of compounds that have transport properties that would not travel through a groundwater pathway from the manufacturing facility to this well. So this fingerprinting exercise clearly differentiates between the manufacturing facility impacts and other sources. And to close on manufacturing, just some operational considerations for manufacturers. It's important that they review material and process operations, their supply chain, how their wastewater treatment plant is operated, what their waste disposal practices are, and the influence of historic remediation systems for past impacts or past investigations. Portfolio screening is important for manufacturers with a large number of facilities. And that's something that we can help with in terms of looking through historic records for PFAS use, the history of releases, the hydrogeologic and hydraulic settings, potential receptors and stakeholders. We have to be able to mitigate liability during remediation or construction, demolition, and dewatering projects. You know, the last thing you want to do is get in there and do remediation or construction and make a bad situation worse. But the only way to do that is to be aware of what the problem is. And you know, all of this has to proceed under the uncertainty of a rapidly developing regulatory landscape, where rules are being developed under significant public pressure. And early engagement on the part of the manufacturers with regulators and stakeholders can make a big difference in the development of these regulations. And I think that's the last slide, so I think we'll turn it over for questions.
Okay, thanks a lot. Thanks a lot, Ross and Stefano. Just while you're thinking about questions, please think them and type them in. I have a few myself. Just before we get to the questions, we just want to remind you that session 3 is going to be next Tuesday at 9 a.m. Pacific, noon Eastern, where we're going to be discussing PFAS at waste management facilities and looking at effective and emerging site management and remediation strategies. So as it says here, we hope to continue unlocking the PFAS puzzle with you. Now, in terms of questions, someone had asked on sources, and this has to do with firefighting in in the West here, certainly in BC and probably California as well. Are you guys aware of any firefighting foams used in wildfires? Forest firefighting that might contain PFAS?
In theory, they shouldn't, but what we came to learn is that during those big operations, various fire departments are involved, and you really take whatever you can get, especially if you're under pressure. So it's not uncommon to find AFFF actually used to fight forest fires in some cases, because that was the supply available at that time.
Wow, that's interesting.
Yeah, I think traditionally dry fuel fires, like a wood fire, would be treated with the Class A foam, the maximum expansion foam. The Class B foams for liquid fires were more expensive and less effective at brush fires. But I would echo what Stefano says, that when you're faced with a big fire, sometimes you use the tools that are at your disposal.
Interesting. So another question here, it has to do with the fingerprinting. I've been involved in fingerprinting with other types of compounds, and sometimes there's a desire to use fingerprinting to see if you can age date. Is there any, you mentioned for example, the PFAS, the C8s were largely phased out, by 2002. So have you ever thought about being able to find out if the release happened, before 2002 as opposed to after? So a question lawyers might ask in some certain cases.
It's a good question, and there are a couple of things that are challenging, but we have been working in that direction. Like, one of them is that the manufacturing was phased out, but the use wasn't in some cases. So it's a matter of exactly find out when they last used them as opposed to when they were last manufactured. But the other interesting thing also is that many of the PFAS have branched and linear molecules, and in addition to just the individual compounds that we discussed before, some of which were phased out, the type of process to manufacture the PFAS changed, and the telomerization process that we talked about, that is more recent, in theory is supposed to produce primarily linear PFAS, whereas the electrochemical fluorination process was producing a mixture of branch and linear PFAS. as well as different type of precursors. So by combining all that, we actually have some tools that can look at the specific composition and support some of the age dating that you mentioned.
Wow, interesting.
Yeah, I would, I would second that. The PFAS can be useful for fingerprinting, but it can also be inconclusive, and it can be very helpful to have other geochemical parameters. And there are more traditional stable isotopes that can be used for age dating that could be a supporting line of evidence to a PFAS fingerprint, given some of the uncertainties Stefano recognized.
So another question I have, again related to sources, but it has to do with wastewater treatment plants and their biosolids. I'm not sure if you can do it anymore, but there have been products you buy in hardware stores. I'm talking about soil, biosolids from wastewater treatment plants that are marketed as nutrient rich to use in your gardens. And now I'm just starting to wonder if I ever bought any of that stuff. Was I spreading PFAS all over my yard? Have you heard any such horror stories? Is it something to be worried about? Or?
Yeah, absolutely. There are a number of sites here in the Northeast where PFAS is being analyzed for around biosolids application sites. And there are some biosolids that are of concern. There are other biosolids that appear to be usable without significant impacts to groundwater or surface water. It requires a lot of screening and a lot of understanding of where the biosolids are coming from. But it can create a big problem when used improperly.
Wow. Oh, wow. That sounds, I'm getting the impression this PFAS thing isn't going away anytime soon.
And relative to biosolids, there's an organization, I think it's Northeast Biosolids and Residuals Association, NEBRA. They've published a lot of white papers and presentations on PFAS and biosolids, and they're a great resource for information on that front.
Oh, really? Maybe if people want to find out, is there a link or something that you're aware of that maybe we can make available to our listeners?
Yeah, we could. Absolutely. Okay,
so yeah, on that note, folks, if you don't have any questions or like right now, feel free to send them into info@geoenviropro.com, and we'll get these guys to fire off some answers for you. Still a couple more questions. One, Stefano, you showed something called a hydra sleeve, and I believe it looked like a plastic tube with a weight on the end. And it's my understanding that it gives you you lower it down in a monitoring well, for example. When you pull it up, it fills up, so you get an instantaneous volume of water from whatever depth you place the thing at. And right. Assuming that's correct, the question I have is for PFAS. That hydra sleeve you showed looked an awful lot like polyethylene. Wouldn't PFAS stick on the polyethylene just like a magnet?
It could, and that's a good question. They actually manufacture a specific hydra sleeve for PFAS sampling. So lots of the suppliers, just not only for hydra sleeve, but balers and pumps and fittings and other equipment, that lots of challenges early on, because many of these materials could contain PFAS like Teflon and so forth. If not directly, potentially manufactured together with other products containing PFAS. So the issue of cross-contamination was there. So they had to reformulate some of their products specific for PFAS sampling. So the hydra sleeve actually have a version that is recommended for PFAS sampling only.
All right. No, I didn't realize that. So there's a whole industry being built around sampling for these things. So you get to, when you're looking at something at nanograms per liter, my goodness, part per trillion, this is a big deal. Maybe that'll be part of the subject of next week's webinar. At any rate, I think we're about at our time here, and I don't think we have any more questions at the moment, but feel free to send in questions, as I said, at info@geoenviropro.com, and we'll get back to you, and we look forward to seeing you next week. And don't forget, tomorrow is our GeoPro Talks webinar. We're going to be talking about Britannia Mine and sustainable development at that mine site. So thanks, everybody. And I'll just say as Guy Patrick saying goodbye, and we'll let you, Stefano and Ross, say goodbye, and we'll call it a day.
All right.
Thank you very much.
Bye-bye, everybody.